Lesson 8.1, logarithms and logarithmic functions. So now we finally get to be using these keys right here on your calculator. One says log, L-O-G, and right beneath that, there's a different key that says Ln. That's a special kind of logarithm called a natural logarithm. So more on that probably next week or so, but let's just look at what is a logarithm, why would you use it? There are a few classic stories that you guys might be able to connect with here. So let me flip a few pages here. There's uh, some investing questions. You guys remember if you have an account that's accumulating interest, that the amount will grow exponentially. But what if you ask the reverse question? Like, for example, I want to have this $1,000 principal turn into $10,000. How much time would that take? Huh. Well, that would be sort of like an inverse question. Or intensity of earthquakes is another example. Or, oh, here it is, pH. Your book does an example of pH, say from chemistry, like how acidic or basic is the concentration. It's something where, say, the concentration or values might span over giant orders of magnitude. I'll show you guys an example of what some graphs might look like. So I just went to Desmos and typed in just real basic logarithm, f of x equals log x. I'll zoom in a little bit here. There you go. Right. And what you might notice is that that's actually the inverse of f of x equals 10 to the power of x. You see that those are both inverses. One way to spot an inverse is that they flip over the line y equals x. Right? So like if this y equals x is a mirror, right? So these two other functions are mirrors of each other, right? Or if you swap the x and the y. Okay, so here, if I look at these two, since we've done a bunch of banking examples, if you had the x, so I'm looking at this black curve right here. If you had the x-axis represent how much time that your principal had been in the bank, so like 2 years, 4 years, 6 years, I'm looking at, right? Then the y-axis could have something to do with how much money is in. Okay, now this is we're growing at a really large clip here. It'd be a ridiculous interest rate, but just to get the idea, that is the basic curve shape, right? But what if you wanted to flip this around and say, hey, I want my value, the value of my money to reach some value, right? How much time is that going to take? Well, that might be able to be more easily answered by this red curve, which is the inverse curve, right? Again, you guys remember inverses if you swap x and y and just resolve it, right? This exponential equation in black turns into this logarithm looking function in red, right? Oh, I said another example I was pointing out was earthquake intensity, right? So earthquake intensity is measured on the Richter scale. So if you open up the news and say, oh, there was a magnitude 6 quake or a magnitude 7 quake, magnitude 8, magnitude 9, say, okay, 6, 7, 8, 9. Oh, okay, so by the time we get to magnitude 10, oh, is 10, let's see, twice of 5? So would that be twice as intense? And no, not at all. Right? So what what the Richter scale of magnitudes are telling you, we're thinking about like factors of 10. So if you look at this here, in terms of the black curve, the Richter scale reading could be on the x-axis, right? So we have a magnitude, 5, 6, 7, 8, 9, 10 earthquake, right? And the y-axis would represent the actual intensity. But you guys see it's going up by factors of 10. So if you have a magnitude 7 quake, that's 10 times as intense as what do I say, magnitude 7, or if a magnitude 7 is 10 times a magnitude 6, right? And the logarithm interpretation, now I'm looking at this red curve, is you could spot some particular intensity on the x-axis, and the y-axis would tell you the Richter scale reading. Right? So here, if I zoom out a little bit, I can make up some values. Let's say, uh, let's go x equals 1. What if you had a Richter scale reading of 1, okay, which is really tiny, but let's say, okay, well, that wouldn't be hardly intense at all. I've never even heard of a reading like that. But how about, let's see oh, whoops, sorry, I'm doing magnitude here. Uh, how about, sorry, I'm thinking the other way. Come out here. Okay, let's say there was a magnitude of, okay, let's say there was an intensity, I should say, of like 10 units, like pressure units or something. Okay, all right, this right here would say, okay, so 10 pressure units on to like a vibrating earthquake could correspond to like a 1 on the Richter scale. Okay, that's what I'm looking at with this red curve. Okay, now what if you had a different earthquake that had intensity, I should say, like an intensity of 100. You guys see 100 is 10 times 10. Okay, so that would be like 10 times as intense or destructive. Well, that gets a rating right here. Boom, you can see the Y value just showed up right there. It gets a Richter scale rating of 2. Here, I'll do one more here. What if you had an earthquake that was 10 times as intense as that one? So 100 times 10, now we're up to 1,000. Ooh, now we're getting really epic. Now I have to scroll way out for this. But there's my line. Okay. Now, the spread line looks fairly flat, but it's not actually flat. I bet this point right here goes up to 3. Boom, exactly. So that would be a Richter scale reading of 3, which would indicate an intensity of 1,000 units of, okay, like earthquake. Okay, all right. So, all right, I'll zoom in one more time so we can compare the exponential curve to the logarithm curve. Again, you guys see that those are inverses, so I can flip it over the line y equals x. Okay. All right, so let's go to the book and see what can we do with that. Okay. Now, your book does a kind of a slow build up. So lesson 8.1, we're really just scratching the surface, and 8.2 gets more into more interesting properties. Right, so okay, so that's another lesson, but one day at a time, I suppose. Okay. Okay, so what you really want to know is what I boxed in here. Okay? Is if you have some exponent form x to the power y equals z, how can you write that in terms of logarithms? Right, so it'd be log base x, so this x takes the place of the base. Okay? To the power of okay, y here, y ends up showing up on the other side of the logarithm. Okay? And what the answer was over here, z, right, that shows up inside the log. Okay? Sometimes I've heard this referred to as rolling the log. I put little quotation marks. That's in official math books, but it seems kind of useful, right? Because you're going to take this question and sort of roll it around. Okay? So you can go back and forth. Okay? So what if you start with a logarithm? You have, okay, log base x of z equals y. By the way, the key on your calculator, the one that says log, is always base 10. So a 10 could go where that x goes. Hey, kind of like the Richter scale intensity that I was just showing you guys with Desmos. Okay? And the other key that your calculator does have stored is the one that says LN, and that's always base E, but more on that probably next week. Okay, so let's mostly stick to probably base 10 today. Okay? But in general, this x could really be any base. Okay? So if I take that base, put it to the power of the answer on the other side, x to the power of y, let's follow over here. Okay? That's equal to what's inside the logarithm, which is z right here. Okay? So it's just different notation. This takes a little while to get used to. You, just run a few examples, and after a while, it'll click in your mind. When it does, now you have a different way to look at like power type equations. Right? Instead of exponential, it's logarithm, they're inverses. Right? There's a nice little inverse relationship showing up right there. All right, so with all of that, let's jump into some examples and then eventually to the puzzles. So example one. Example one. All right, we got write each equation in exponential form. All right, so looks like they're giving us some logarithms. We're saying turn that into an exponent. So if you have log base 4 of 64, that's equal to 3. Okay? Now, the way I could write that in terms of exponents, okay, is all I have to do is follow my model right here. Okay? So they gave us this. I said I'm going to take the base x, which is like here, which in this case 4, to the power of the other side, which in this case is 3. Okay? And that's equal to this inside bit right here, which is 64. Okay? So that's exactly what they want you to do. Now, is that a true statement? See, 4 to the power 3, that's 4 times 4 times 4, isn't it? 4 by 4 by 4. Is that 64? Oh, yeah, it totally is. Bing, it worked out. One thing's a little weird about this. How do you deal with this like base of 4? Because again, the calculator only has either base 10 or base E. Here, I'll show you guys one way to handle it right now. I'm jumping ahead a little bit. Okay. But this is the same thing, by the way, as log. I think I'm jumping to the next lesson, but that's all right. Okay, you guys get a little extra info here. Log of any base of 64 divided log of the matching base of 4. Okay. That should also be the same thing. Let me show you guys that's true. So if I do parentheses log of 64, now switch to base 10. Okay, that's okay. All collectively divided by log base 10 of 4. See, now it should say 3. If it says 3, then I've been telling you the truth. Oh yeah, equals 3 also. Check. By the way, you also could have done natural log 64 over natural log of 4. Okay, let me show you that works also. You guys should replace the log base 10 with natural log. Do that for both of these. As long as they match. Yeah, that's also 3. Check. Okay. So a little extra there. What's next? B, we got log base 3 of 1 over 243. That's all equal to -5. Negative, that's what's saying. You know what I should have mentioned about negatives is there are domain and range restrictions on exponents and logarithms. Here, let's take a quick look at that. You guys see that for this black curve exponential function, there's no domain restriction, X could be anything, but the Y values, well, there is a range restriction from, well, anything above zero, so only positive values, right? Well, the inverse is true for logarithms. Logarithms, like the parent function, typically the domain is restricted to only positive values, but the range could be anything, okay? Right? So for example, with earthquakes, the ground, like once the ground starts vibrating, how much pressure is involved is only a positive value, hence the positive domain, right? But the Richter scale reading could be like anything. It could go from negative infinity to positive infinity. And typically the ones that show in the news tend to be like between like 6 and 10, like somewhere there. Right? All right. So about that. All right. Okay. So is it okay for this to be negative? Yes. A logarithm can have a negative y value. That's okay. Okay. Um, let's see, how can I rearrange this and put this in an exponent form? Well, just like before, I'm going to take, here, find my model here to show you guys. Okay. What I'm going to do is take this base right here, which is 3, put it to the power of the other side, just like here, just follow this back. So it's 3 to the negative 5 equals 1 divided by 243. Okay. Blah, blah. Example A was a real statement. So is this also a true statement? Or are they both true? Okay. Well, 3 to the negative 5. Hey, isn't that like 1 divided by 3 to the 5? Okay, I know that. 1 over 3 to the 5. Okay, that's what a negative exponent does. It makes it a fraction. So is 3 to the power of 5? Is that the same thing as 243? Yes, it is. So check, check. It's all looking good. Okay, so what's example C? We got log base 9 of 3 equals 1/2. All right, so same as the last couple, I'm going to take this base 9, put it to the power of the other side, 1/2, and that should be equal to 3. Oh, well, 1/2 power. Actually, that's kind of special. Isn't that a square root? So square root of 9 is equal to 3. Is that true? Is the square root of 9 3? Yeah, totally is. Yeah, so good. All right, check, 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 check. This is all working out. Okay, so now you guys have a, again, new notation to work with exponentials, but now it's the inverse. Let's keep checking through these examples. What's next? Example 2. Write each equation in logarithmic form. So we got 7 to the power 6 equals 117,649. Okay, so this is exactly backwards of example 1. Example 1, they gave us logs and asked for the exponent form. Here, they're giving us the exponential form. Example, can you write this as a logarithm? So we're just going to translate the other way. So we're going to take the 7, that looks like the base. Okay, so to go log base 7, okay, of z, so of the other side, so that's of 117,649, okay, is equal to this power right here, which is 6. Yeah, that's good. Right? Of course, you can roll the log back and forth. So 7 to the 6 is 117,000 something. That's what we were doing before. Yeah, there we go. Right. Oh, another advantage of logarithms I meant to mention is that this is another. You guys notice that what used to be in a power here, 6, is no longer in a power anymore? Yeah, right. So back in module 7, there were a few puzzles where you had to solve for x from an exponent, and then there are certain ways to do that, certain limited ways. If the numbers are nice. What if the numbers aren't nice? You can actually use logarithms to solve like wicked looking puzzles, like children should do. Okay. Now I think before this would be the same thing as log base e 117,649 divided by log base e of 7. Okay. So let's see, is this really equal to 6? Let's see if it is. So let's do log base e, ln, 117,649 divided by log base e, or ln of 7. If this says 6, we're still good. Oh yeah, check, check. It sure is, sure is. We are winning. How about these other ones? So that was 2a. How about 2b? We got 8 to the negative 3 equals 1 over 512. Yeah. So I can follow my model right here. I'm going to do log base 8 of 1 over 512. And that should be negative 3. Yeah, that checks out, I think. Okay. The next lesson, it actually tells you how to take logs and fractions. All right. You can treat this 1 over 512 as 512 to the negative 1. Here, I'll go ahead and write this out. This is for, I think this is all we're looking for. Okay. I'm showing you guys some extra tricks that you're going to use in the future anyway. This log base 8 of 512 to the power of negative 1. Okay. And another cool thing about logarithms is that if you have logarithm of something to power something, you have to take that power in front. So again, your book saves this for lesson 8 too. Just show you guys a little at a time. So I'm claiming that negative log base 8, you know what? Calculator doesn't have log base 8, so I'll change that to, let's do base 10 of 512 divided by log base 10 of 8. Here's the same trick as I used up here. Okay, that should be equal to -3. Okay, let's see if it is. See if it is. So negative log of 512 divided by log of 8 is, yep, it totally is -3. Check it, check it, check it. Oh yeah, we are winning. All right. So I think the book was just really wants you to be able to do this right now. I just showed you a little extra stuff to confirm that this is all true. Okay. Let's do example 3. Evaluate logarithmic expressions. Log base 216 of 6. What could that possibly be? Well, I'll call it x. Let's say we're like solving for x, right? What is x, man? Well, I do know I can use this rolling the log trick and maybe turn this into an exponent. Let's just play around with that and see if that leads anywhere. 216 to the power of x is equal to 6. So now what? Well, 216, that looks like 6 to the power something. So let me play around with that a little bit. What's 6 to the power of 2? Oh, actually, no, that's it. All right, so 6 to the 3. So where the 216 is, I'll replace that with 6 to the power of 3. That's still the power of x equals 6. Okay. Uh, okay. And then a power to a power, I can combine the powers. Okay, so 6 to something equals 6 to the 1. That must mean 3x is equal to 1. Divide both sides by 3. X is 1/3. All right, that should be the answer. Oh, yeah, yeah, that's also what your book got, 1/3. Okay. And you could plug this back into the original statement. I'll try it this way. It's natural log of 6 divided by natural log of 216. That should be also a third. Let's see if that's true. If that's true, then it's all matching up. Natural log of 6 divided by natural log of 216. See if I get a 0.33333330. Oh, yeah, sure do. Ba-ding. All good. All good. Example 4. Inverses of exponential functions. We got a story going on here. The air pressure outside an aircraft can be determined by the equation P equals B multiplied by 10 to the negative 9H over 100. That looks like it's all in the power there. Where B is the air pressure at sea level. So we'll point to that, I'll call it sea level pressure. I think sea level is 2 words, whoops. And H is the altitude in miles. H, okay, is the altitude in miles. And okay, if it is P the pressure? Air, oh yeah, okay. This is air pressure outside an aircraft. Right? Air pressure outside aircraft. All right, so yeah, let's try this, right? Like, what if your altitude was 0? Wouldn't that be sea level? So if you plug a 0 here, this whole thing becomes 0, 10 to the 0 is 1, and then 1 times sea level pressure is sea level pressure. Okay, that checks out. Okay. And it looks like the higher you're going, now you have a negative exponent. 10 to a negative exponent gets smaller, smaller, smaller. Okay, and the pressure's getting less and less and less. Yeah, that checks out. All right, so if the air pressure at sea level is 14.7 pounds per square inch, write an equation to find the height of an aircraft. Ooh, yep, just like I told you guys. What we're solving for, we're about to be solving for, it starts out stuff in the exponent. Hence, logarithms are about to be really helpful for this type of question. Okay. Of an aircraft when the pressure is known. Okay, when the pressure is known, yeah. So P is some known pressure. We'll call it like a variable. Right? We'll plug in 14.7 pounds per square inch for sea level pressure, okay? Which is true. The air pressure you're sitting in this room. Hey, isn't a bowling ball, a pretty heavy bowling ball, about 14, 15 pounds? Okay? You have about that on every square inch of your skin right now, sea level. Yeah, pretty crazy, but true. And so plug that in and we're solving for H. So say P equals 14.7 psi, pounds per square inch, times 10 to the negative 9 h we're solving for over 100. Okay. Since what we're solving for is in the exponent, let's get it out of the exponent by applying a logarithm. Um, I should think of the way I just explained that. I realize is your book is kind of waiting for lesson 8.2 to get to that. Here. All right. But that's okay. We can solve this the other way. Right? What I'm thinking of is actually this one right here. Okay. So this line right here. But here. So let me go ahead and divide over 14.7 first. So P divided by 14.7 psi, right? So, already this is looking like a ratio, right? What's the pressure inside or right outside the plane at a high altitude compared to sea level? Maybe it's like 70% or 50%, whatever, like 0.7 over 0.5. So it's 10 to the power of negative 9 h, which is the altitude overnight. Okay. So now we can apply a logarithm. So I'll take a log of both sides. So log base 10 of the left side equals log base 10 of the right side. Okay. Okay. And when I do that, this log 10, okay. Whenever you see a log base here and the inside value base, they match, right? It's sort of like a cancellation. You can think of it that way, right? And the answer ends up being this power here. Okay. I don't know if that made sense, but I'll write the answer for the next step. So log base 10 of the outside pressure compared to sea level pressure is equal to negative 9h over 100. And it's no longer an exponent. Right? It's just down here with everybody else. Okay. Uh, which means now we can just use regular algebra 1 rules to finish this off and solve for h. I can multiply both sides by negative 100 over 9. Okay, so times negative 100 over 9. Do that to both sides. Negative 100 over 9. Okay. Right, and that'll give me the answer. So h is equal to negative 100 over 9 times log base 10 of the outside pressure over 14.7 psi. Okay. Okay, so what could this be useful for? Well, imagine you're a pilot up in one of these aircraft, one of these airplanes, right? And maybe it's night outside, you can't really tell how high above the ground you are, but you do have pressure detecting equipment. And your pressure detecting equipment says, hey, the pressure outside is like 11 pounds per square inch. Like, okay, right, if this number is 11, I can feed it into this equation and it'll tell me my altitude, it'll tell me how far above sea level I am. Aha, and that could be useful. Let's see what this looks like in Desmos. I haven't done a graph in a while, so here, I'll clear all this out. Now, what forms do I want to put in Desmos? Um, let's start with that book form right there. Right now, B is come on here. Can I expand this? Yeah, there we go. All right, so I'm going to treat the outside pressure as y and h as x, and then later on I'll switch them, and they should be inverses. Okay, so I'll say y equals 14.7, right, multiplied by 10 to the power of, right, negative 9x instead of h. I'll call it x, but I'll switch that later. Over 100. Okay. Uh, okay. Actually, I wonder if I leave it as P and H, if Desmos would handle that. Let's see, they should. Yeah, it should. Okay, so I have a P-axis versus an H-axis. Pressure is a function of altitude. And look, this totally makes sense. So if you have an altitude of 0, so you're at sea level, your pressure is 14.7 pounds per square inch. Okay? And as you increase in altitude, say like, what did they say it was in miles? So if you're like 10 miles up, that could be this X value here is 10 miles up. Now there's very, very low pressure, right? But again, what if you had the reverse question? So you have all this plane equipment that tells you the pressure outside. It says, oh, it's like 11 pounds per square inch. Like, hey, I want to know what my altitude is. And that is the inverse, which brings us exactly to this logarithm. Okay, so here's what we got before, or well, from pineapple. Right. So now my x and y are changed. Now this h altitude is going to become my y value. Well, I'll just call it y. Right. I think Desmos will recognize this. Let's see. And then I'm going to call it pressure to the x value, right? Like my independent variable. So, whoops, over 9, right? Multiplied by So log is on log base 10. And then where the P pressure goes, I'll put X because that's my variable now for 14.7. Okay, I think I should do it. 100 over 9. There we go. I wanted to change this to blue because I realized those two curves inverted. Okay, it could get kind of messy which one's which. Okay, so the red one is the original exponential function. It's pressure is a function of height. Right? This blue one is the logarithm that I just made. Okay? And that's height is a function of pressure. Okay? So let's do that example of what if x equals 11. Right? So your instruments tell you the pressure outside is 11 psi. Okay? And then wherever it crosses the blue one specifically. All right, so your altitude would be about 1.399 miles. Let's call it 1.4 miles. Okay, now you're 1.4 miles above sea level. Okay. Hey, by the way, what if the pressure outside was 14.7 psi? Shouldn't your altitude be 0? Okay, let's see. Oh, did it go away? Well, 14. Is that? Okay, yeah, I don't know why I was glitching like that. Okay, there we go. Right, so that's it right there. Right, so again, yeah, if the pressure outside is 14.7 pounds per square inch, that corresponds to 0 altitude. Yeah. Right, there we go. Right. So two different curves going on right there. There we go. All right. So switch back over here then. Um, okay. Ooh, got an example of tornadoes. That looks pretty fun. Do that. Okay. Example 5, graph. Well, I just did some graphs with you guys, so let's see what they have to say here, what they want you to figure out. Graph each function, find key features. So log base 6 of x. Yeah, when you ever just like y equals log x or whatever base, it tends to look like this hook pattern. You guys just saw a few curves that look like that. So basic logarithm right there. Okay. How about some individual coordinates? Like if you plug in, here, I write this on paper so it's a little bit bigger. Okay. Y equals log base 6 of x. Remember, that's the same thing as 6 to the power of y equals x. And so, hey, we could always make an xy table, right? Let's do that. Let's just plot a bunch of points and then let's get out. Sorry. So x, y. What do I want for to be like x or y? Okay. Well, this exponential looks a little more familiar. We've been doing a lot more of these recently. Hey, maybe I could find some different values of y and see what naturally comes out for x. So let's go -1, 0, 1, 2. Let's try this, see what happens. Okay. So if I plug in -1 for x, or sorry, for y, I mean, I'll get 6 to the -1, which is 1 over 6. If I plug in 0, you think 0 is 1. 6 to the 1 is 6. 6 squared is 36. Okay. All right. So, so, okay. But you notice that even though y values in this case are allowed to go positive or negative, that's okay. There's no range restriction. There is a domain restriction. It looks like all my x values naturally came out positive, and that would always have to be the case for this basic logarithm, unless you like apply a bunch of shifting around or something. So now my x-axis, you got to scale all the way to 36. Let's go like 10, 20, 30, 40. Okay. And then y, let's go 1, 2, 0, and 1. So yeah, I think this will be able to handle everything here. So let's plot these points. So when x is 1, 6, y is -1. That's yeah, that's about right there. Boink. When x is 1, y is 0. It's pretty close to right there. Boink. When x is 6, y is 1. That's about right there. Boink. 36, 2. Let's write it right here. Boink. Yep, that's that classic hook shape right there. Classic hook. Oh, yeah. Okay. And there's a vertical asymptote on the y-axis. And the equation, of course, for that would be x is equal to 0. That's the vertical asymptote. Yeah. All right, there we go. All right, and inverse to that. Can I do that? Flip the paper trick, the inverse? Yeah, does that show up on camera? Sort of. Yeah, it looks more like a classic exponential, doesn't it? The inverse. There we go. Um, okay. Here, yeah, let's look at transformations of graphs right here. Transformations. So if you have g of x equals 2 log base 10 of x plus 3, and then the whole thing minus 1. Okay. Well, what if the parent function, I'll call f of x, was just plain log base 10 of x? Okay. Right. So real basic graph, right? Kind of what we just did for log base 6, except instead of this point right here being 6 comma 1, and maybe it would be 10 comma 1 for log base 10. Okay, it looks like this. Okay. Well, we're looking at transformations. So I think this plus 3 means go to the left 3. This 2 times in front would stretch vertically by a factor of 2. And this minus 1 tag to the end says go down 1. Okay. Yeah, so you can shift this around here. I'll put both of those graphs into Desmos to show you guys that that would be the outcome. All right, so let's clear all these out. Clear, clear. All right, let's go f of x is equal to just log x, so log base 10x. Okay. You know what I'll do while I'm at it? Let me change this setting. Let's go y-axis from like -1 to 2 should do it. Right. All right, let's go back. Yeah, okay, that looks better. Okay. And okay, and then what we're gonna do, no, keep in mind my axes are skewed, right? Okay, so the x-axis, I see 0 to 20, y-axis 0 to 2. Okay, so keep that in mind. All right, so g of x, I'm going to be translating around. So it's 2 times, so it's going to be like twice, whoops, g of x equals 2 times. So now it's going to be like twice as tall. Okay, I still have log base 10. I can just write log, right? Base 10 is assumed. Right, x plus 3, so that's going to send it left 3. And the whole thing minus 1, I should go down 1. Okay, yep, that's just what it looks like. I said that black curve is about twice as tall as that blue curve. Shifted left 2, like this point right here is at, okay, is at 1, 0, right? But if you go left 2, down 1, so left 2, down 1, let's see, is that this point right here? Yeah, -2, -1. Right, that's exactly it. Yeah. Left 2, down 1. Okay. Oh, well, okay. And then vertical stretch. Right. Okay. You have to consider that too. Right. Anyway, there we go. Here's some translation. Vertical translation. Okay. We consider all these factors. Okay, go on. All right. Write each equation in exponential form. So book puzzles. Log base 15 of 225 equals 2. All they want you to do is to write this as the base of 15 to the power of 2 equals 225. That is true, isn't it? 15 squared, 225. Check. Number 4. Log base 3 of 243 is equal to 5. Well, I think I would write it as 3 to the power of 5 equals 243. Is that true? Is 3 to the 5 is 243? Yeah, that's true. Yeah. I do a little bonus right here. What if I rewrite this as natural log of 243 divided by natural log of 3? So let's do that. Natural log of 243 divided by natural log of 3. Yep, it's also 5. Yeah, it all checks out. All checks out. Number 7. Write each equation of, logarithmic form. Now we're going the other way. 2 to the power of 7 is 128. Okay. So I think that log base 2 of 128 would be 7. Now that's what they want you to write, but how do you know if that's true or not? Let me use this log trick I did before. Natural log of 128 divided by natural log of 2. As long as this tells me 7, then that worked. ln 128 over ln 2. Yeah, it is 7. It is 7. Oh, yeah. Now, number 10. All right, so we got 1 over 7 to the power of 3 equals 1 over 343. Okay. I'm tempted to throw in a negative exponent and just flip everything non-fractions, but if I take it directly at face value, this could be log base 1 over 7. It's kind of weird. Of 1 over 343 is all equal to 3. Okay, yeah. If you want to check it with this log trick, a couple times you can do that too, but it's got to work out. 7 to the 3. Yeah, okay, that was right. 13. Evaluate each expression. Log base 2 of 64. What is that? Well, I'll just say it's equal to x, and we'll solve for x. Yeah. So if you roll the log trick, 2 to the power of what we're looking for is equal to 64. Right? So let's see, 2 times what? 2 to the power of 1 is 2. 2 squared is 4. 8, 16, 32, 64. I think x has to be 6. Okay. That was kind of a ham-fisted get and check way, but here, let's make sure that's right first. 2 to the 6, yeah, the 64. So that is true. Okay. But the way I might do it, we'll do this in the future, is I could do natural log of 64 divided by natural log of 2. That should also be x. Let's see. Natural log of 64 divided by natural log of 2. Yeah, it is 6. All right, different way of looking at it. All right, so there's a couple of perspectives there. 16 log base 27 of 81. Okay. So roll the log, 27 to the x equals 81. Okay. Well, I know 27 and 81 both have like 9s or 3s in common. Let me go all the way to 3. Let's just see what happens. Let's see, 3 times 3 is 9 times 3 is 27. So I think 3 cubed is 27. Look like that. Equals, then it's like 3 to the 4. Oh, you know what? Actually, maybe I'm doing this the old way. Okay, 3 to something equals 3 to something else. I think 3x has to be 4. So x has to be 4/3. That should be the answer. Make sure that works. Okay, so 27 to the power of 4/3 is 81. Check, 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 check. Okay. How could you write this as a logarithm? I would do log base 27 of 81 is equal to x. Okay. Or for that matter, you could go natural log 81 over natural log 27. Okay. So this could also solve it. Let's see if it does. So natural log 81 divided by natural log 27, 1.333, which is 4/3. Check, check. Oh yeah, win. So 16, 19. Log base 8 of 512. Hmm. Right, so I could go 8 to the x. Okay. Now I do see this 8 and 512 are both powers of 2. 8 is 2 cubed. 512, I think it's 9. Let me see. 2, 4, 8, 16, 32, 64, 128, 256, 512. Yeah, that is 2 to the 9. Okay. So 3x must be 9. Divide both sides by 3. X is 3. Okay. Alternatively, natural log of 512 divided by natural log of 8. That's another way to say x. Let's see, the calculator also gives me 3. It should. X equals, come on, 3. Natural log of 512 divided by natural log of 8. Oh yeah. Check, check. It's the same thing. Checks all over. 22. Electricity. Electric current I in amperes of a particular circuit can be represented by this expression. So go well, actually it's in a logarithm. Maybe we should start with that. So log base 2 of the intensity, a little Ceres on that, equals negative t, where time is in seconds. So I stands for electric current. Oops, what am I thinking? Sorry, I always said that. I'll say current, electric current, and t is time in seconds. So current is in amperes, time is in seconds. Okay. Write an equation when to find the current when the time is known. Okay. So like the way this expression is given to you is if you, let's say you had an ammeter and you were directly measuring the current. Oh, we have 2 amps or 3 amps, right? It can tell you how much time has passed, right? You can determine that. Okay. But what if you want to know, or what if you do know how much time has passed? You want to know, okay, well, what's the current build up to in amps? Okay. That's conceptually what we're going for. So I need to solve for I, which represents current. So I think 2 to the power of t, that's what I is. Uh, or sorry, negative t. Okay? And that could be the answer itself. So I could be 2 to the negative t. Right? But you guys also remember negative power is the same thing as fractions. So I could do that. Okay? So here's 2 different ways to write the correct answer. 2 different ways to do it. Pick your favorite. 24. Graph each function, determine the key features. Here, I'll go ahead and pop this in Desmos. So, but you could always make a table. I got y equal. Actually, maybe I should show you guys that first. Log base 9 nope, 1 over 9. Log base 1 over 9 of x. Okay. So let's make a table. I'll graph it and then I'll open Desmos and show you guys that I'm telling you the truth here. So let's do x, y. Okay. Well, you say I could rearrange this. I could say, hey, I know that 1 over 9 to the power of y is equal to x. So let's pick some values for y. How about -2, -1, 0, 1? See what happens. So if I plug in 0, anything to the power of 0 is 1. If I plug in 1, anything to the power of 1 is itself. -1 turns into a fraction. -2, 9 squared is 81. Just look like that. Yeah, it's kind of great. Definitely one of those log looking graphs. So the domain, I just need the positive values of x. The range could be anything. Okay, let's go up to 81, huh? Let's go 20, 40, 60, 80, 20, 40, 60, 80. Okay, and then the y values, -2, -1, 0, 1, 2. Okay. Put some points here. So when x is 81, y is -2. Y is -2. Yeah. Okay. Y is -2. Let's type right here. Okay. When x is 9, which is way back here, y is -1. When x is 1, y is 0. Type right there. And when x is 1/9, y is 1. Okay, so yeah, this is going to be an upside down looking logarithm. Okay. It still has a vertical asymptote on the y-axis at x equals 0. Uh, Still looks kind of flat. It will have a range of anything from -infinity to infinity. The range is unrestricted. Okay? But it is like an upside down logarithm. All right, so let's see what that does that look like in Desmos. Clear all this out. Clear, clear. All right. Well, how can they do log base 1/9? One way to do that is to do uh, natural log of x. Whoops, this is not clear. Okay. And then take that and divide by, oh, come on. Don't do that to me. There, come on here. Natural log of x, all divided by, there we go. Natural log of 1 over 9. Okay, boing, boing. Okay. Yep, that's exactly what I just graphed, isn't it? That looks like it. Yeah, same thing. Okay. Oh, we've even got the, yeah, okay. Oh, yeah, why did it turn upside down? Well, one way to think about it, and your book really introduces this next lesson, is that when you have a log of a fraction like this, like 1 over 9, you can express that 1 over 9 is 9 to the -1. You can take the negative out. So if I change this 1 over 9 to negative sorry, to 9 and I pull the negative out. That's what I should do. It'll create the exact same curve. So watch this. I'm going to get rid of this and call this 9, okay? And then bring the negative in front of the whole thing. And it's the same curve. It's the exact same curve. Like I said, yeah, that's a trick for next lesson, but you guys see it a little bit early. Same thing. Oh, yeah. All right, let's keep winning. All right, okay, so key features here. I see a domain from, well, x is strictly greater than 0, range is unbounded, and there's a vertical asymptote here at x equals 0. So and x-intercept here at 1, 0. All right, so those would all be features. All right, 26. I got f of x equals log base 2 of x. Okay. Here, gonna take a little shortcut. You could totally make a table out of this, like we did for the last one. I'm gonna go straight to Desmos. The same thing as natural log x over natural log 2. All right, let's do Desmos. See what's that look like. All right, so natural log x over natural log 2. So, okay, so all that's really changing is this changes to 2. Of course, we got rid of this negative, so that's gone. Okay, so that's what your graph looks like. Yeah, there's a classic looking logarithm graph, just like that. Okay. Now, what does the base 2 mean? Well, if I zoom way in, probably has something to do with, okay, well, that intercept is classically going to be 1, 0. See, what other point could I have? Um, yeah, let's poke around a little bit. Let's see what happens. So 2 to the 1 is 2. Okay. What if x is equal to 2? Watch this. Okay. It crosses exactly here. Aha, at 2, 1. Okay. Because again, 2 to the power of 1 is 2. Okay. Hey, what is 2 squared? That would be 4. If I change this to 4, I bet that just bumps us up to the next integer value. Yeah, so y is 2. And then that's the power to, well, 8. So watch them going 2, 4, 8, 16. And look, the y value keeps going up by 1. Now we're up to y is 3. I bet if I change this x to 16, the y value is 4. Let's see. If I change this to 16, is y equal to 4? Oh, yeah. What if I change this to 32? Is y equal to 5? Oh, yeah. There we go. All right. So you can test that there. I just don't like that. All right, back over here. That was 26. All right, let's do these 3 word puzzles. One for pH and chemistry, acidity, one for earthquakes, and one for investing. And then I'll wrap up this video. And so some good word puzzles here. Biotech, the pH of a substance can be represented by this equation. Okay. So they're saying y equals negative log base 10 of, and then in brackets here, which represents a concentration, H plus. Okay. Where H plus is the concentration of hydrogen ions, or including brackets, so concentration of hydrogen ions. Okay. And okay, which usually varies between 10 to the negative 14 and 1 mole, or although it doesn't have to, right? But typically it's there. Again, this Y is the pH. Go ahead and label that. Okay, pH. Okay. For example, lemon juice is acidic. Okay. And the concentration of hydrogen ions is 1 times 10 to the negative 2. Therefore, that has a pH of 2. So the lower pH values correspond to something that's very acidic. Let me show you guys that your book is telling you the truth. If I do negative, log, and then for the concentration of hydrogen ions, I'll do 1 times 10 to the negative 2, which is just 10 to the negative 2. This should tell me pH of 2. Yeah, it exactly does. That's definitely a pH of 2. All right, so we got that. Household bleach has a pH of 13. Oh, that's extremely basic. The kind of the tipping point where you go from acidity to being basic is pH of 7. So pH of 7 is neutral. Okay? And that corresponds to the concentration of hydrogen ions being 10 to the negative 7. Okay? I think like a medium concentration, not too little, not too much, kind of like a Goldilocks. Right? And so I get like tap water. But if I very simply go up here to 10 to the negative something and for negative 2, I'll put negative 13. Okay. Now we have pH of 13. That's extremely basic. That's household bleach. Okay, graph the function. List any constraints on domain and range. Yes, check this out. So, all right, let's go. Concentration of hydrogen ions is H plus. That's like my X value. And I'll call pH my Y value. So this is like X in quotation marks. This is like Y in quotation marks. So instead of an XY axis, I'll have an H plus and pH axis. Yeah. Right now, the concentration of hydrogen ions, I think, has to be positive. Like it cannot be negative. Right? It probably realistically can't very much go to 0. I think we're hitting an asymptote there. But maybe it could go from like, let's do 1, let's do 3, 7, 10, 14. I wonder if we can go above 14. Let me do 15. Let's see what happens. Okay. pH scales tend to go from, or sorry, wait, what am I thinking? Sorry, wrong way. ignore what I just said. But we're gonna get rid of that. I was trying to tell you guys some pH values. Okay, that's not concentration. Okay, get rid of all this. Okay, although okay, here. Okay, let's go pH values. Okay. Now pH can go negative. So what if I rearrange this equation? I can say this here. I'll put this in pinky here. I'm just gonna find an inverse type equation. So if I take the negative to the other side and I take 10 to that negative power, that's 10 to the negative pH is equal to the concentration of hydrogen ions. This is in the inverse equation. Okay. Now, what I wrote in pink and what I wrote in blue correspond to the same information. It's just backwards. Okay. So let me try it this way. Can I go a pH of -2 or 0 or 1 or 7? Let's do 14. Let's do 15. Okay. And I'll see what the concentration of hydrogen ions should be. And I'll use my pink inverse equation here. So let's go 10 to the power of, now two negatives cancel. Negative, negative, that'd be like 2. So this would be like 100, which is extreme, right? Like if you had a concentration of hydrogen ions that was like 100 mole, that would be extremely acidic. That's why the scale usually even starts at 0, although it's not technically bounded to 0. Right? So the extreme pH. Now if I do 0, 10 to the 0, again following this model here, I get 1. Right? That's also still extremely acidic. Right? It's 100 times less acidic than a pH of -2, but it's still extremely acidic. Okay, now what if I plug in 1? Now, keep in mind, I do have to have a negative here. So this is like 1 over 10 or 0.1. Okay. 0.1 is 1 over 10. Okay. How about, what if I do 7? Okay, well, now we have 10 to the -7. So 1, 2, 3, 4, 6, 7. Yeah. Okay. This would be 10 to the -14, 10 to the -15. Okay. Now, once you get up to a pH of like 14, 15, that's extremely basic. So you're not bounded by 14. pH doesn't have to stop at 14, but charts typically stop there just because it gets so extreme at that point. Okay. Yeah, what does this graph look like? I'm going to put the concentration of hydrogen ions on the x-axis, and let's do pH on the y-axis. So go like that. Okay. Concentration of hydrogen ions, it has to be positive, and you can go up however big, right? But yeah, right. Once you hit like a pH of 0, which is like 1, yeah, that's getting pretty extreme up there. Right, so I'll just put a 1 right here. Right? And my 100 is going to be 100 times further to the right. That's like out this room and into the hall, right? Okay, so not space my graph, but you guys see what they do. Okay. And the pH, well, pH can go negative or positive. I have it going up to 15 here. Let's go 5, 10, 15. Okay, let's go like -5, whatever. Okay. Okay, let's plot some points. So the 1, 0 is a point that we are here. Boink. Okay. 1/10, 1 is a point. That's like 1/10, 1. This is going to be a strange looking graph. That's okay. We'll make do. 10 to the -7, 7. Okay, well, from here on out, okay, 10 to the -14, 10 to the -15. Okay, those numbers are so close to 0, right? We're talking about like less than winning the lottery as a chance, right? Right, so we're running pretty fast into this vertical asymptote right here. Okay. Okay, now going to the right, this graph will cross through 1, 0. It's going to look like that, basically. Okay, so it's a little skewed, but basically, yeah. Okay. So basically, there you go. Okay. So when you're told, oh, this water bottle has a water with a pH of 7, like, okay, pH of 7, okay, and that could correspond to some concentration of hydrogen ions here. Sort of. All right, so got chemistry, pH. Let's go to 44, earthquakes. The intensity of earthquake. Can you go through with the Richter scale? Richter scale. 44. Formula y equals 10 to the r minus 1, where y is the absolute intensity, and r is the Richter scale measurement. There we go. Now, this one, your book gave you the exponential form of the equation. So I'm going to guess maybe they want you to solve Richter scale in terms of intensity. Let's just do that anyway, whether they ask it or not. So I can take log of both sides. So log base 10 of the intensity. It's also, remember, y is intensity, okay, is equal to, well, that would just be r minus 1 is what it would be. Remember, 10 to the r minus 1 is y, and so on, okay, where r is the Richter scale rating. So if you simply add 1 to the other side, you can get the Richter scale number in terms of the intensity. So Richter scale rating is, well, I'll say 1 plus, okay, log base 10, and, well, okay, y, but I'll go ahead and spell it out. Intensity. Okay. You can sort of think of intensity like pressure. It's sort of scaled like that, right? So like what's the pressure of rocks like vibrating for an earthquake, like that, property or weight. And so we got this looking equation, right? And so your book gave you the exponent, exponential equation, which tends to look like this. Okay, that's intensity as a function of Richter scale reading. Okay? And you can rearrange this the other way around. So then I would get see Richter scale rating as a function of intensity. Now the intensity has to start at 0, but it can go really big. And the Richter scale values, well, again, if you go from like a Richter scale magnitude 6 to a magnitude 7, the intensity is actually like 10 times as much to the right. All right, so what we're looking at. So what did they actually ask for here? Graph the function, determine key features. Okay, well here's a little. Yeah, maybe I'll. Okay. Here, I'm gonna throw these into Desmos. Okay. I have little ones mocked up there. You guys get the idea what it looks like, but let's see what Desmos has to say. Okay. Notice for these graphs, I've been keeping my y-axis shortened there, which has been really helpful for these logarithms. Okay. All right, so let's do this way. Y equals 10 to the power of x minus, whoops, what did I just do? X, no, I forgot I had to do this, to the power of x minus 1. Okay, right. So in that case, y would be the intensity and x is the Richter scale. And let's do it the other way around. Let's do, oops, I had it boxed in right there. There we go. Right. So in place of r, I'll put y for now it's the Richter scale reading equals 1 plus log base 10 of the intensity, and I'll call that x this time. Okay. So again, these two are total inverse of each other. Right? What is y and what is x? So in one equation, x is Richter scale rating, y is intensity. In the other equation, it's the reverse. Okay. Here, I'm going to do this too. Since they are inverses, I'll go ahead and change my axes back so you can see a direct comparison there. Let's change this from like -5 to 5. Let's change this one from -5 to 5, and I'll just scroll out from there. That should equalize my axes. Yeah, see how they're definitely inverses? You definitely see that. Okay. What are these intercepts right here? Like this intercept is at 0.1. This intercept is it should be at 0.10. Yeah, there we go. All right. Okay, and I see a horizontal asymptote on one and a vertical asymptote on the other. Horizontal asymptote, of course, on the exponential equation, and vertical asymptote on the logarithm. All right, so we got all that. Oh, good. And then it said 1906. Yeah, there was this famous earthquake in San Francisco. Absolute intensity of 6 million units. What was the Richter scale reading? So right here, I'm just going to put 6 million like intensity units. I think it's in watts, I want to say, but regardless, let's throw that in the calculator and see what the Richter scale reading would be. So 1 plus log base 10 of 6 million. That would be a Richter scale rating. This is question C of 7.778. Let's call it about 7.8. There we go. Okay. So there you go. Richter scale rating of almost 8, which is a really massive earthquake. Yeah, that's so there. Don't want to be in the city during that. All right. Last one. Ooh, investing. Okay. Maria invests $1,000 in a savings account that pays 4% interest compounded annually. The amount after some number of years is this expression, which, yeah, we've been working with these. The amount as a function of time in years could be the principal of $1,000, okay, multiplied by, and 1 plus the interest rate. We've got 4% interest, so this shows up as 1.04. Okay. This is all power to t, the number of years that have passed. Simple letters. Yeah. Oh, that's good. All right. So now if she held money there for, say, 8 years, 9 years, 10 years, she can figure out how much money is going to accumulate. But what if you had the reverse question? What if you want to know, hey, I want my $1,000 principal to become like $5,000. How much time is that going to take? Well, you can set this up to solve very quickly with a logarithm. So here, I'll call this A. Okay. So again, C divided over 1,000. So A over 1,000 principal is 1.04 to the power of t. Okay. And then I can apply a logarithm. So log, let's do base 10. A over 1,000 is equal to, see, oh no, what am I doing? This is my base, 1.04. There we go. 1.04. Right, that's all equal to t. There we go. So that looks right. Okay. This is probably what the book is looking for, but that's not so nice in the calculator, so let's make that nice in the calculator. So I'm going to switch to log base 10, and then of a, all divided by, or whoops, sorry, a over 1,000. Yeah, a over 1,000. There we go. All divided by a log base 10 of 1.04. Okay, that's also t. Okay. And you know what, since I had a divided by 1,000 up here, okay, there's another logarithm rule that your book was going to save for next lesson, but I'll show it to you right here. If you have a log of a fraction, that's the same thing as a difference of logs. So I can take advantage of that here. I can say log of the target amount minus log, base 10 of 1,000 over log base 10 of 1.04 is equal to the amount of time that will take to accumulate. Okay. Actually, you can do another trick here, which is also next lesson. This 1,000 is related to 10. If I do log of 1,000, I just want to show you guys this bit. It should be 3. Yeah, it is, because 10 to the power of 3 is 1,000. This bit right here is the same thing as 3. Okay. So with all that in mind, let's pick a target value and run it. Okay? So what if I was shooting for $5,000? Okay, how much time would it take to reach $5,000 from $1,000 principal? So I can go log $5,000 for targeting minus, well, this is 3, so I'll just call it 3. And then divide that by log of 1.04. Okay? It's telling me that for the amount to go to $5,000, the time would be 41 years. Right? Now, let me try that backwards the other way. So if you left the money for 41 years, it should be pretty close to $5,000 in terms of the exponential equation. See, that's true. Take $1,000 principal times 1.04 to the power of 41 years. And yep, there's $5,000. Oh yeah, oh yeah. So that'll be a wrap on 8.1. All right, and next coming up will be the next lesson.